Alrighty, so give me just a minute to save this. So I'm doing things slightly differently today because of all the technical difficulties that I've faced with Zoom over the last several days. Or not Zoom specifically, but just the internet in our classroom. And now, for whatever reason, oh, I know why it's not working. I didn't plug it in. Alrighty, so in addition to recording the lectures on Zoom, I'm also trying to record it using a screen capture thing so that if the internet craps out, which seems to happen fairly often for me in this room, I will still have a recording of everything that we're talking about that I can upload so that everybody gets everything. Yeah, all right, so let me share my screen. So what we're going to do today is similar to what we did on Friday. I have a hard problem from an old test that I'd like us to work together as a class. And then once we get finished with that, I'd like the students to work, those students who haven't completed the in-class assignment to work on that. And then when they get specific questions, ask those of me, not just ask, how do I work this problem? Because as I've stated previously, I'm not going to be there on test day to work problems on the board, so you better get used to doing them yourselves. All right, so the lecture for this material was about mesh analysis. So what is the first step of mesh analysis technique? Anybody recall? Identify our meshes. So in this case, I'm going to call this guy mesh current 1. This guy mesh current 2. This guy mesh current 3. And this guy mesh current 4. So I believe I've done steps 1 and 2, identifying our meshes and labeling our meshes. So a mesh current is a current that flows around a small loop in a circuit. It isn't necessarily a current that flows through a specific element. And so what I mean by that is if we look at mesh current I3 in the bottom left-hand loop of the circuit, the current I3 flows into the negative polarity terminal of the 90-volt source. And it's the only current that flows through the 90-volt source. So if instead we looked at the 40 ohm resistor though, we would see that mesh current I3 is the current that flows down into the positive polarity terminal of the voltage drops Vx. And mesh current I4 is the current flowing up through the 40 ohm resistor into the negative polarity terminal. So we could say that the total current flowing through that 40 ohm resistor with direction down is I3 minus I4, and the total current flowing up would be I4 minus I3. So that's what I mean when I say a mesh current doesn't specifically flow through a single resistor or single component or something like that. There can be multiple mesh currents. Okay, so in this problem, we are going to try to solve for the current Ix, the voltage drop Vx, and then lastly, the power supplied by our dependent source. Those are our 3 quantities of interest. And the reason why I ask 3 questions like this is because that's what I typically do on a test problem as well, so that you get a little bit more bang for your buck out of a particular circuit analysis, right? There's a limited amount of time, so if you can analyze this one circuit correctly and give me 3 pieces of information, that should take you a significantly shorter amount of time than analyzing 3 discrete circuits and answering 1 question on each of them. So this is the format that you should be getting used to seeing. All right. So in this particular problem, there are no super meshes because there are no interior current sources. However, there are 2 current relationships that we're going to have to write. Every time we see a current source, whether it's on the interior of the circuit or the perimeter of the circuit, we're going to have to write a current relationship equation. So let's start with those guys. All right, so how can I relate the top left current source to the mesh currents that are flowing around in this circuit? So I hear that I1 is equal to 4 amps. So let's talk about why that's correct. As the current I1 goes around this triangular path, it's going to be flowing from left to right as it goes across the top portion of its mesh. That is in the same direction that is indicated by the current source, which is why I1 is directly equal to 4 amps. If we look at the top right current source, what relationship should we get? Somebody that isn't that young lady over there. Yeah, so we'll see that I2 is equal to -2 amps. And again, this is because as this current flows around its mesh clockwise, we'll see that our mesh current is flowing from left to right through the top portion, which is in the opposite direction indicated by the 2 amp source. So since it's in the opposite direction, we need to include that negative sign. Now, let's write our Kirchhoff's voltage law equations. All right, so starting with mesh 3, and I'm going to start at the bottom left-hand corner of the mesh, as I always do, and then follow the mesh current clockwise around its loop. So what's the first thing that I see following mesh current I3 around its clockwise path? All right, so it's the 90-volt source. Do I see the negative polarity terminal or the positive polarity terminal first? The negative polarity terminal. So that means I'm going to have negative 90 volts. So it's the exact same rules as we discussed when we covered Kirchhoff's voltage law. What do I see next? All right, so the 20 ohm resistor. What is the total current flowing through the 20 ohm resistor? And we are going to be specific here, we are going to assume that the current I3 is flowing into the positive polarity terminal when we're performing Kirchhoff's voltage law around for mesh current I3. And so we're looking at positive polarity here, negative polarity. So what's the total current? I3 minus I1, all right. And what do we see next? 40 ohm resistor, all righty, so plus 40 ohms. And what's the total current through the 40 ohm resistor, positive polarity on top? I3 minus I4, and set this equal to 0. Let's see what's in chat. Why didn't I include the power source in the relationship equation? So that's a great question. We can't write a Kirchhoff's voltage law loop around mesh I1 or mesh I2 because they contain current sources. So the reason why we can't write one is because the voltage drop over a current source is entirely independent of the current that's being provided by those voltage sources. Because that dependent source happens to be in between those two meshes, which we can't write KVL equations for, that's why it's not going to show up in anything that we've done. We know everything that we need to know about those particular meshes because we know how much current flows through them. And so what I mean by that is, let's erase this. And let's erase this guy as well. If I were to ask you guys how much current is flowing through that dependent source, you actually have enough information to tell me what that answer is, as long as I specify a direction, without doing any actual mesh analysis. So for instance, if I ask for the current direction down, what's it going to be? 6 amps, 4 amps plus 2 amps. We just apply Kirchhoff's current law at this node. So the dependent source doesn't even need to be in our equations because we know everything. We know the current that's going to flow through it already. Is that a satisfactory explanation, Ms. Robles? She's not saying no, so I'm going to move on. All right. So, yeah, okay, great. All righty. So we have written our KVL equation for mesh 3. Now let's write it for mesh 4. So we're going to start at the bottom left-hand corner, which is right here. So what's the first thing I see? So here's why I don't like negative. So you're saying the negative sign because we're looking at the negative polarity terminal of the voltage Vx. But when we're doing mesh analysis, we're putting everything in terms of our mesh currents. So that voltage Vx is really inconsequential at this point. We're going to circle back around to it. The reason why I don't like to include things like that in my first section of equations is because I find it to be confusing, actually. Like I'm trying to get everything in terms of the mesh currents as much as possible. And in this particular case, I expect that all of the contribution of the current I4 will have a positive value, and throwing a negative sign in front might make things a little bit confusing. So we see the 40 ohm resistor first, and the total current. Now we're looking for the current flowing up through that 40 ohm resistor as we follow mesh current I4 around its clockwise path. So the total current flowing up is going to be what? I4 minus I3. There's nothing inherently wrong about saying it's negative 40 ohms times I3 minus I4. That's just confusing to me, and I'm trying to get you guys into good habits, I guess. All right, so what do we see next? The 10 ohm resistor. And what is the total current flowing through the 10 ohm resistor? And I guess in this case, we're looking from left to right. So we're looking for this current, so I4 minus I2. What do we see next? And do we see the positive polarity terminal or the negative polarity terminal first? Positive polarity terminal. And now we're back to our bottom node. So we start at one potential and we end at that same potential. So we now have 4 equations, and we could do direct substitution. Everywhere we see I1, we could call it 4 amps. Everywhere we see I2, we could call it negative 2 amps. So let's go ahead and do that real quick. So let's see, I'm going to have my first equation. I'm going to have 20 I3 plus 40 ohms I3 minus 40 ohms I4 is equal to 90 volts plus 20 ohms times 4 amps is 80 volts. And let's see, I don't have an I2 in there, so I've taken care of this guy, this guy, this guy, this guy, and this guy. So that's all of the different pieces. And we could simplify that further if we needed to, but the calculator will take care of everything for us. In our second equation, we're going to see negative 40 ohms times I3, which takes care of this guy. We're going to see positive 40 ohms times I4, which takes care of that guy, plus 10 ohms I4, takes care of that guy, 10 ohms times negative I2, so 10 times negative 2, 10 times positive 2, that's going to be 20 volts. When we move it to the other side, it's going to look like negative 20 volts. And when we move 120 volts to the right-hand side of the equal sign, that's going to be minus 120 volts. So to start things off here, did I make any algebraic mistakes? Because if I did, then obviously our answers are going to be incorrect. Anybody see anything glaring that I made a boneheaded mistake about? It does absolutely happen, so don't feel that I'm going to punish you in any way for correcting my mistakes. Not good. Algebra seem legit to everybody? All righty. So we have those two equations in a form that we can throw them into our calculator and solve. So we should find an answer for I3 and some answer for I4. And when somebody gets an answer, please let me know and I'll see if it matches mine. The last voltage on the first equation is 80 volts, and it comes from 20 being multiplied by I1, which is 4 amps. So 20 times 4 amps is 80 volts, or 20 times negative I1 is minus 80 volts. And then when we move it to the right-hand side of the equal sign, that's where we got positive 80 volts. So anybody solve their 2x2 system of equations yet? I got something different than that, so I could have typed something wrong as well. So let's see if anybody else comes up with anything. So we have 3 different answers. So I'm going to go back through and check my system. So just to be clear here, so my coefficient for I3 in the first equation is 20 plus 40, which is 60. My coefficient for I4 is negative 40, and my constant term is 90 plus 80, which is 170. Alrighty. And then my coefficient for I3 in the bottom equation, or in equation 2, is negative 40. My coefficient, oh no, there's definitely a mistake in mine as well, because my coefficient for I4 should be 40 plus 10, and I just had 10. Then my coefficient for the constant term is negative 20 minus 120 is negative 40. So let's solve. And I get positive 2.071 amps for I3 and negative 1.143 amps, which I believe is what you got. Great. So those are the answers that I got for I3 and I4. So now that we know what all of our mesh currents are, how can we solve for our three quantities of interest up here? So how do we solve for IX? So it's not negative I4. It's the current flowing, the total current flowing down through the 40 ohm resistor, right? So we can't ignore the contribution from mesh current I3 as well. So it should be I3, because I3 is flowing down, minus I4, and it's minus I4 because I4 is flowing up. So I3 minus I4, which is 3.214 amps. How do we get Vx? Exactly right, just using Ohm's law. So we know all these currents, whenever we want a voltage, we're just going to have to use Ohm's law. Just like when we did nodal analysis, we knew all the voltages. Whenever we needed a current, we used Ohm's law to find that. So Vx is simply 40 ohms times Ix. So let's multiply this guy by 40. We get 128.571 volts. And lastly, we want the power supplied by the dependent source. So that is going to be, we need the current flowing into the negative polarity terminal, which is going to be what? So we found the current flowing through the positive polarity terminal earlier using KCL. Now we want the current in the opposite direction. What do we do? Negative, right? So negative 6 amps times 0.2, which is our coefficient, times Vx of 128.571 volts. I get negative 154.286 watts. So what does it mean that the power supplied by the dependent source is negative? It's absorbed, right? So all that really means is that my best guess is the 120 volt source is supplying. I'm not sure exactly what's going on with the 90 volt source. It may be supplying, it may be absorbing. Typically speaking, the largest source usually winds up supplying. All right, so what did you guys think about that problem? Difficulty levels seem extreme or moderate or easy? Pretty moderate, okay, yeah. So this is fairly representative of the type of stuff that I may ask you on your exam. This one more so than the question we talked about with the nodal analysis, which again, I thought was fairly mild, but apparently I am a glutton for punishment and also a jerk. So, all right. So with that example problem out of the way, I'd like for you guys to again use the next 25 to 30 minutes to be working on any in-class assignment problems that you weren't able to complete. If you have any questions about anything, you know, feel free to let me know, but for now, try to confer with people sitting at your table. Garrett and Mr. Wickland, is that right? Yeah, since you guys are being lone wolves, why don't you cut that crap out and work together? And if the two of you would care to join any of the other tables of 2 people, of which there are multiple, to work on it as 4, please feel free to do so, assuming the people at the table are okay with that. Alrighty, so what we're going to do today is work an old problem from a test regarding mesh analysis. As soon as we conclude our analysis of this problem, this doesn't really work well for the students that are in the room. But class students, I want to do what we get on
Friday. As much as I want you guys to work together on any problems that may not have been, we'll finish.
And then when you have questions, let me know and I'll come by. For those of you that are on Zoom, I can see when you ask a question in chat as I walk around the room. So if you have any questions about the in-class assignment problems, let me know and we can look at them on the computer. Alrighty, so this is a a mesh analysis problem. And so who among you can remember what the first step in mesh analysis is based on the video lecture? Identify our meshes. So I'm going to do steps 1 and 2 together, identify the meshes, and label the meshes. And so I'm going to call this top left triangle mesh 1, and I'm going to give it a mesh current I1. The top right triangle will be mesh 2. The bottom left triangle will be mesh 3, and the bottom right triangle will be mesh 4. So when we use nodal analysis, we saw that it was really kind of a shorthand method of identifying voltages with respect to a particular point in the circuit. Mesh currents are similar in as much as they don't necessarily refer to the current flowing through a specific element. They are the current that flows clockwise around these particular paths. So the path that mesh current I1 is going to take would look something like this, right? It's this clockwise triangular path around all of these elements. So we could see, for example, that across that 20 ohm resistor, and I'll do the mesh 2's current path in a slightly different color. Like this. So we can see that through the 20 ohm resistor, there are actually 2 mesh currents flowing. Both I1 and I3 flow through that 20 ohm resistor simultaneously. So when it comes time to write our equations, we are going to have to indicate a specific direction that we are interested in. And that direction, let's talk about that real briefly here. So if we were following mesh current I3 around that bottom left-hand mesh, we would say that I3 is the positive current, and any mesh current that is opposite the direction of I3 through a particular branch then gets a negative sign. If we wrote our mesh equation or KVL equation for mesh current I4, we would expect I4 to be positive and anything in the opposite direction of I4 to be negative, and so forth. All right, so with that out of the way, let's identify our quantities of interest in this problem. The first thing that we're going to try to solve for is our current IX, which is not a mesh current. We are going to try to solve for the voltage Vx. And lastly, we are going to try to solve for the power supplied by our dependent source. All right, so in nodal analysis, for every voltage source that we had to write a voltage relationship equation. In mesh analysis, for every current source we have, we need to write a current relationship equation. So we have 2 current sources, which means we should have 2 current relationship equations. So, sorry, that's my recorder telling me the battery is up. So for the 4 amp source in the top left of the circuit, how can we relate that given current of 4 amps to the mesh currents as they're drawn on our schematic diagram? So it's just I1. All right, so the reason why that's true is that we can see as mesh current I1 flows along the topmost path of its mesh, it's in the exact same direction as the direction indicated by the current source. So that's why I1 is equal to 4 amps. For our 2 amp source, what's our current relationship equation going to be? Negative I2. That's absolutely right. And if I draw this, so when I2 is flowing around that topmost portion of the mesh, it's flowing from left to right around its clockwise path, which is in the opposite direction of the 2 amp source. So that's why we say 2 amps is equal to negative I2. Now, because these two current sources are along the perimeter or the outside of the circuit, we won't have a Kirchhoff's voltage law relationship to write because we haven't formed a super mesh. Super meshes only occur when the current source is on the interior of the circuit. So instead, now we'll get our other two equations from Kirchhoff's voltage law around meshes 3 and 4. So starting at the bottom left-hand corner and writing a KCL equation for mesh 3, what do we see first? So we're following mesh 3 around its mesh current I3 around its clockwise path, starting from the bottom left-hand corner of the circuit. We're just writing a
Negative 90.
negative 90. Thank you. So negative 90 volts. What do we see next? The 20 ohm resistor. And the total current flowing through the 20 ohm resistor is going to be some combination of I1 and I3, okay? So what we're trying to find when we're writing our mesh current or our KVL equation around mesh 3 is the current's going to enter into the positive polarity terminal. Mesh current I3 will be thought of as entering the positive polarity terminal of all of our resistors. And again, anything that's opposite that direction is going to be a negative sign. So in this case, I3 enters the positive polarity terminal and I1 enters the negative polarity terminal. So that voltage drop is then simply 20 I3 minus I1. So using that same convention, who can tell me what's going on with the 40 ohm resistor? $40 ohms times I3 minus I4. Absolutely correct. And we've ended at the same potential as we started. So we set everything equal to 0. So now let's do the same thing for mesh current I4. So we're going to start at the bottom left-hand corner, which is right here, and then follow the clockwise path of the current around its loop. So what's our first term in our equation going to be? It's going to be 40 ohms. We see a 40 ohm resistor first. What's the total current flowing through the 40 ohm resistor? So yeah, we should be considering I4 to be positive. I4 minus I3. Now there may be some confusion here because that's opposite what we would expect with the voltage drop Vx defined in there. But Vx is an entirely different bag of cats here, okay? So when we're writing our equations, we want to put everything in terms of our mesh current. The Vx will come along significantly later. All right, what's the next thing that we see? Our 10 ohm resistor, all righty. And what's the total current flowing through the 10 ohm resistor? I4 minus I2. So you hesitated and said plus, and so I just want to point out that as long as all of your mesh currents are in the same direction, so if they're all clockwise or they're all counterclockwise, you should never have a current plus another current, okay? At least as far as your KVL equations go. So if you mismatch things and all that kind of stuff, then you may have plus signs, but if you're consistently in either clockwise or counterclockwise direction, it'll always be one current minus another current. Alrighty, what do we see next? 120 volts. Do we see the positive polarity terminal or negative polarity terminal first? positive. Yep. So there we go. And now we've ended at the place where we began. So we have, we set it equal to 0. All right. So now we have 4 equations, 4 unknowns, but we can do some simple substitutions. So since 4 amps is equal to I1 and I2 is negative 2 amps, so let's just slightly rewrite that guy. It'll make the substitution slightly easier in my head. We can write an equation. So for instance, we see 20 ohms times I3 plus 40 ohms times I3 minus 40 ohms times I4. So I've taken care of this guy, and this guy will be equal to positive 90 volts when I move that over to the right-hand side. And then I'm going to have 20 times negative I1. So 20 times negative 4 is negative 80. When I move that over to the right-hand side of the equal sign, I get positive 80 volts. So that's equation 1 rewritten. Spell that 1, and this guy then 1 prime. This guy will be equation 2, and we're going to rewrite this one. So our coefficient for I3 is negative 40 ohms. A coefficient for I4, positive 40 ohms, and positive 10 ohms. So we've taken care of this guy, and this guy. And I2 is negative 2, so we have 10 times negative negative 2. So 10 times positive 2 is positive 20 amps, or excuse me, positive 20 volts. When we move it over, we're going to have minus 20 volts. And when we move the 120 volts over, it'll be negative 120 volts. And this is equation 2. And so now we have 2 equations, 2 unknowns, which we should be able to solve for unknown mesh currents, I3 and I4. So take a few moments to familiarize yourself with the equation solving tools on your calculator and tell me what these numbers are supposed to be. Has anybody gotten an answer yet? Alrighty, that is what I got as well. So now that we know what all of the mesh currents are, let's circle back to the quantities that we are trying to solve for. Okay? So, what is the current IX in this circuit going to be in terms of mesh currents? Current directed down through the 40 ohm resistor. Right? So, how do I relate that to the mesh currents? That is absolutely correct. I3 is in the same direction as it flows through the middle branch. I4 is in the opposite direction. So Ix is simply I3 minus I4. So that is 3.214 amperes. How are we going to solve for the quantity Vx? Okay, so Ix times the 40 ohm resistor. Yeah, so just Ohm's law, right? So using Ohm's law, 40 ohms times Ix gives me 128.571 volts. Alrighty, and the last question here is, what is the power supplied by our dependent source? I'm going to need to erase a few things here because we're going to have to talk about this. So, as some of you have likely noticed, our dependent source did not show up in any of the equations that we wrote. And in a moment, it should be fairly obvious why that is. But for right now, I can explain that apparent omission as follows, right? If we try to write a Kirchhoff voltage law equation around either mesh 1 or mesh 2, we would have to include the voltage drop over a current source, right? Because there are current sources in each of those meshes. The problem there, and this is the reason why the super mesh technique exists, which I addressed in my video lecture, is that the voltage drop over a current source is entirely unrelated to the current that's being supplied by the current source, okay? There is no simple current voltage relationship for sources like there is for resistors, and then we'll find out later capacitors, inductors, etc. So because these current sources happen to be on the perimeter of the circuit, we had simple and easy relationships, which we addressed here and here. Now, what we want is the power supplied by this dependent current source, which means we are looking for this current. Does anybody have any idea how we might determine what that current is? So 0.2 times Vx is the voltage drop over that voltage source. The amount of current flowing through a voltage source is unrelated to the voltage drop over the voltage source, just like the amount of voltage over a current source is unrelated to the current. So 0.2 Vx isn't going to help us find the current in any way, shape, or form, right? When we have a source, the current and the voltage are independent of each other. So what if I drew my arrow for my current right here? Does that change your opinion on how we might approach this at all? Yeah, absolutely. So we could do KCL here, which we could do based on what we know. Wouldn't be particularly difficult, but it would be tedious. If we do KCL at this node instead, it's actually rather trivial, right? Because we know that 4 amps plus 2 amps plus this unknown current has to equal to 0. So the value of the unknown current is 4 plus 2 plus x is equal to 0. What's x? -6, right? So that's our current flowing into the negative polarity terminal based on Kirchhoff's current law at that top node. Now we multiply this by the 0.2 Vx because we're trying to find the power. And power is voltage, which is 0.2 Vx, times current, which is -6 amps. So we get 0.2 times 128.571. Sorry, let's include units here. And we get let's see, 6 times 0.2 is 1.2, so 154.286 watts. Negative. Yes, sir. So if we apply Kirchhoff's current law, I'm not sure that I understand your question. Yeah, so all three currents are going in. So 4 plus 2 plus the unknown current have to be equal to 0. When we move the 4 and the 2 to the other side, exactly right, yeah. Right, into the negative polarity terminal, and we're trying to find the supplied power. So that's why we tried to find the current flowing into the negative polarity terminal specifically, because we wanted supplied power, and supplied power is current goes into the negative terminal, absorbed power is current goes into the positive terminal. All right, so what did you guys feel about the difficulty of this problem? Was it easy? Was it moderate? Was it difficult? Okay. Was it difficult? Okay, so somewhere between easy to moderate, or maybe between moderate and difficult, but not difficult. All right, so this problem is very representative of what I put on a test. This is actually an old test problem. I changed a couple of the numbers, but it doesn't particularly matter. So what I like to do on exams, and I'm saying this because you guys have an exam in exactly 1 week. Hopefully you are aware of that. If not, you are now. So you've got an exam next Monday night. And what I like to do is I like to put a particular schematic diagram up and then ask 2 to 3 questions about it, so that you don't have to analyze 20 separate circuits. You have to analyze significantly less. That does mean that if you make a simple mistake on one circuit, you can lose a lot of points because there are multiple questions asked about it. But from a timing perspective, it's much less work on you guys to be able to solve, 20 questions on maybe 8 circuits or so in 2 hours than 20 questions on 20 circuits in 2 hours. So this level of difficulty and this level of leading questions. So particularly, I asked what I feel is something pretty easy first, finding the current. Then once we know the current, finding the voltage one step further. And then there's the harder part, which is usually going to be some sort of power relationship. And I will just give you fair warning, I am absolutely enough of a jerk to put both the positive and negative answers for power and make them available, so that you need to know fundamentally the difference between absorbed power and supplied power. That will pop up on all 3 of the exams in this class, guaranteed. All right, so with all that out of the way, you got about 25 to 30 minutes left. So for those of you that have worked the in-class assignment, just like Friday, if you worked it, feel free, take the rest of the day off. If you haven't worked it, talk among your peers. And if you have any questions about anything, I'll walk around and answer any questions. And again, for those of you that are on the online section, or not an online section, but you happen to be attending class via Zoom, just throw something up into the chat, and I'll see an orange flashy light or whatever, and I'll come address your question momentarily.